Welcome students, and in today's video we are going to talk about something called a matrix exponential. Yes, the motivation to study matrix exponential has been done in the earlier video. In this video we are going to define what matrix exponentials are, and to do that we are going to start with some preliminaries, right? So let us recall what a norm is. Norm of a vector. So given a vector, let's say, yes, let us assume that given a some vector x in Rn or something like this, yeah. So what do you say, what do you think the norm is? So the norm, maybe I can put it like this. So the norm from Rn to R plus, what I mean by this is R union 0. Okay, R plus, so the set of all those the positive reals in union 0. Okay, so the non-negative numbers, that is. So this function which satisfies the following, right? What are the properties? Following properties. So any function which satisfies the following properties is called a norm. What is the first property? The first property is the positivity property, that if you take any element of it, the norm of x is always going to be greater than equal 0, and equality holds. Equality holds if and only if x equals to 0, right? So what is the second property? The scaling property. So under scaling cx, it becomes mod c times norm x. Okay, see, this is the norm. That is what we are defining, norm. Okay, it is for a vector. So for vector, essentially what we are going to do, roughly speaking, we are basically like trying to look at the distance, yes, or the maybe the length, you can say distance from the origin, or the length of x, that is whatever. Yeah, so this is basically the length of the vector x. Yeah, you can think of it like that. So the length of cx will be the modulus of c times norm of x. Yeah, because this is always defined in c plus, right? So this holds for all c in R and x in Rn, right? Number 3. The important property is this property, which is called a triangle property. So this says that mod of x plus y is less than equals to mod x plus mod y, right? This holds for all x comma y in Rn. Okay, so this is what norm is. Of course, if you are given, so given, there are many ways of defining a norm function, right? So basically any function which satisfies these three properties is a norm function. Now given let's say x in Rn, yeah, x in Rn. So what is the norm of so basically you can think of the length of x. Okay, norm of x, this you can define it like this. See, generally speaking, we just write it like this, right? In general books, whatever you have studied, we just write it like this. You can do that, but most of the times I'm just going to put one bar like that, because it is already understood, well understood. So that is why I don't want to do the extra work, but essentially it is all written like this. Let me do it first and then we'll remove the other bar. So here the difference between this is, see, x, then this norm is in Rn, right? That's in Rn, and this is in R, the mod is in R, right? So exactly the same kind of thing, but one thing is in R, one is in Rn. So mod norm of x, that is going to be defined as, of course you can define it like this. So this is the 2 norm, okay? We call it a 2 norm, okay, the Euclidean norm essentially. That is I equals to 1 to n xi square, right? That's what we know. Of course you can define the infinity norm and the 1 norm and any LP norm. How do you define a p norm? P norm is basically you just replace 2 with p. So this is p and this is the pth power, okay, 1 by p essentially. Okay, so those things are there. You guys are familiar with these things. Okay, I'm not spending much time there. Just the the basic notations which we are going to use as a recall. Okay, So given x, we define something like this. The two norm of x is like this, and generally this is called the Euclidean norm, right? Euclid. So after Euclid, let me write it. This is called the Euclidean norm. Clear? And if you take mod of x, that is given by root over x times x. Okay, mod of x, where we define where the inner product, how do you define an inner product on in Rn? The Rn is defined by x comma y. Okay, it is essentially xi yi I equals to 1 to n. Clear? Okay, so the inner product is defined like this. Of course, this is also given by something like this, right? The norm of x times the norm of y times the angle between those cosine, the cosine of the angle between those two. Okay, so where theta is the angle between x and y. Clear? Okay, so all these things are known. All of this is known. Now what we are going to do is write down inequality, which is called a Cauchy-Scwartz inequality. It is very important in our study. I'm not quite sure whether you have you know this thing or not. So I am going to do it properly. Okay, Cauchy-Schwarz inequality. Okay, what is Cauchy-Schwarz inequality says? So it is probably, see, there are some fundamental inequalities in all of mathematics. Okay, Cauchy-Schwarz is probably if not the one, at least the top three fundamental inequality, you can say. Okay, so for, let's say, any xy in Rn. Clear? So you start with any two vectors xy in Rn. Okay, and if you want to look at the mod, this is in R, right? This is the norm. You see, whenever I am taking the inner product of x and y, okay, that becomes a real number. So I am taking the the modulus of that real number, that is always dominated by the norm of x times norm of y. I think this is clear. X and y are a vector in Rn, but whenever I am taking an inner product, that inner product becomes a real number. So here this norm is basically the mod. So norm becomes the modulus in one dimension, right? So this becomes a mod. So this is one dimension, and this is in Rn. Okay, so this this norm is defined in Rn. Of course, this is the 2 norm. Okay, for here now we will just concentrate on the 2 norm. Okay, and the question is this: when is the equality true? Okay, so the inequality is strict unless one of the vectors is a multiple of another. So that is not a very difficult thing to see. Multiple of another, right? So of course, if one is a multiple of another by the scaling property, you can see that the equality holds. There is nothing much to do here. We are just we will just concentrate on proving the theorem. So the proof of this is not very simple. I won't say it is like a trivial proof. Okay, the proof is, first of all, see, if either x and y is 0. Okay, so let's say if y is 0, let's just take y. See, here x and y are interchangeable, right? They are like there's a symmetry working here, so it does not matter. So let's say if y is non-zero here, okay, what happens if y is non-zero? Equality holds. There is nothing to prove here, so equality holds. if y, sorry, if y is 0, I mean non-zero means if y is 0, huh? If y is 0, see, if y is 0, what is the inner product of x and y? 0, and the right hand side is also 0, so the equality holds, huh? There is nothing to do. Okay, now so let y is non-zero, huh? Y is non-zero. Then what we are going to do is choose c, okay, such as to minimize minimize this function g of c, which is x plus cy square. Okay, so I what I'm let us understand what we are trying to do. What I am trying to do is this. See, essentially I chose y non-zero, okay, and I have defined a new function. Okay, so define a new function g of c, which is given by this particular thing. Okay, so if you do that, therefore see what is g of c. G of c is, this is I'm writing it like this, but it is assumed to be, so you see here, this is a norm, right? I am writing it like this. Okay, for now also let me again anyway write it, huh? Okay, so this, if you break it up, it becomes 2c, the inner product of xy plus c square norm y square. I hope this is fine. How do you get this thing? I mean, no, I mean, this is basically the inner product of x plus y times inner product of I mean x plus cy times x plus cy, right? Inner product of x plus cy with itself. Okay, and when you use the inner product properties, you get this sort of thing. Huh? That's okay. And clearly, you see, as a function of c, this is differentiable. I mean, there is nothing to do here, right? Okay, so once it is differentiable, what happens? G prime c becomes 2x comma y plus 2c norm of y square. Okay, so basically what am I doing is I want to choose a c which minimizes gc. Okay, I want to see that whether you can get a I mean whether you can get a c such that this happens. See, this c, the point of all of, I mean there are too many c's here, huh? So how do I put it? See, essentially what am I trying to do is I have two vectors x and y. Okay, I do not want to, and see here x and y is in Rn, right? Huh? I do not want to work with vectors in Rn. What I am going to do is, so I reduce this whole thing to a function in R. So essentially what am I doing? I am taking that, I am assuming that how do I put it? So I'm defining a real valued function, okay, which is given by g of c, which is norm of x plus cy square. Okay, so where is g defined? G is defined from R to R plus, right? R plus, of course, union 0 is there. So R plus, whenever I writing, it is the positive part, union 0, of course, that is there, yeah. Okay, so this thing is there, and here it is quite clear that it is differentiable, and once it is differentiable, this happens. Now I want to see that I want to minimize this g. I want to see what is the I mean, if there is a point where it is taking a minimum. Okay, so you see, if that is the case, then that is equals to 0 in a so let's say for a critical point, so and of course let's assume what is g double prime of c. It is 2 times norm y square, okay, which is always going to be greater than 0 since y is non-zero. Clear? So what is happening here? If you do something like this, then for a critical point c star, critical point c star, g of c star, okay, which is given by this is going to be 0, right? G prime of c star is going to be 0, right? So g prime of c star is going to be 0. So that will imply that c is going to be the inner product of xy by norm y square, right? That is your c. So for, at a critical point, C star G prime of C star is going to be 0, because that's the definition of critical point, and C is given by this. So basically C star, maybe let's just write C star is given by this. Okay, now if C star is given by this, you see, if you put this C star in this, so that will minimize G, right? And what is the minima of G? That is always greater than equal 0, right? The minimum of G is always non-negative. Okay, so let's just put it there, and when you calculate this thing, I mean, I'm not doing all that calculation, but I mean, this is quite evident that if you want to write it, x plus C star y square, that will be the mod x square minus square by norm square. Okay. So that is going to be this. Clear? Okay, and since this is greater than equal 0, hence what do you have? You have Cauchy-Schwartz follows. Okay, CS follows. Is this clear? See, at the minima, at this square can never be negative. So this is always greater than equal 0. And what is the minima of this thing? The minima is that C star, if you just put the value here, then I mean, you can calculate. This is very easy to calculate. Okay, so please calculate it yourself. So DIY. Huh? It's a one line thing, nothing to do here. Okay, just calculate, so you will get it, get this thing, and this will give you that the mod of the inner product of x and y, this is always dominated by norm of x times norm of y. That's Cauchy-Schwartz inequality, right? Okay, now the one thing, one small motive thing which I want you to notice is this. See, there is nothing special about x and y in Rn, right? I mean, of course, I mean, x and y has to be in such a way that they are, the inner product of x and y is defined, right? So that is true. But otherwise, if you just assume that the x and y are belongs to a proper inner product space, so what I mean by this is in a suitable inner product space, then this Cauchy-Schwartz inequality actually holds. The whole theory, I mean, whatever we are doing, this actually holds, right? Of course, you know, it has to be a non-linear space, right? You know, x and y has to be, all of these things has to be, I mean, defined. But once it is defined for some space, let's say if you have a space where x and y, the norm is defined, you know, and you have a inner product defined on this thing, then what you can do is you can do this, you can show that the Cauchy-Schwartz inequality holds. So it's not a special property of Rn, okay? It can hold for other vector spaces also. Okay, so this is just an observation. I mean, fine. So that is the norm. Yeah? Now you see, we are going to finish this video here, but before doing that, one small detail is this. You see why we are doing all these things, because let's say given, the requirement is this. Our requirement is this. Requirement is given A, okay, some matrix A, which is a matrix from linear map from Rn to Rn. Okay, I want to define what is the norm of A, right? Norm of A. So basically, this is, you can think of this as a you know, I mean, how do I put it? Maybe norm may be thought of as the size of A. Size of A. Clear? See, A is a matrix, right? It's a linear map from Rn to Rn. You guys already know that linear map of Rn to Rn, there's an isomorphism between this and a vector space, an Euclidean space. What is that Euclidean space? R to n, right? R to n. So, if you have Rm, let's say A is from Rm to Rn. Okay, so that will, this is basically, I mean, if you look at the linear map from Rm to Rm, that will be isomorphic to a, you know, vector space which is of dimension mn, right? Okay, so and basically that is Rmn kind of thing, yeah, yeah. So see, the point is this. So that's a vector. Essentially, you can think of this as a vector. Okay, you can think of it's not a vector, but you can think of it as a vector, and I mean, we can define, you can try and define a norm on that thing. This is what we need to do. Okay, and we are going to do it in the next video.